Everyone, and today we're gonna solve a question that was asked in GATE 2026. I think this exam was conducted today, and this is the memory-based question. It is given that P is a reflection from R3 to R3 through two dimensions of space, and then they are asking what is the value of 2 to the raise of P minus 3 times determinant of P. Now, since here they have not mentioned anything about the two dimensions of space, so we can take any two-dimensional subspace and try to find out the P, and then we can determine what is trace of P and determinant of P. So this is just to answer the question in the exam. Otherwise, we can try to prove for any two-dimensional subspace that what gonna be the trace and the determinant of this reflection matrix. So first, we're gonna take a simple two-dimensional subspace in R3, and then try to find out what will be the reflection matrix. So let us take the two dimensional subspace S equals to x, y, and 0, where x and y are. So clearly we can see here that z component is 0. So that means S is a two-dimensional plane and it is nothing but the xy plane. So now we can draw the xy plane here. So this is the z component, this is the x component, and this is the y component. So a reflection of a point, for example here, x, y, z, with respect to this xy plane is xy of minus z. So reflection can be seen like kind of a mirror where you are seeing the image on the opposite side with equal distance. So like the z component has got only flipped out. That is the sign of the z component only has got changed because xy remains same. Because xy lies like lying on the xy plane and it belongs to the subspace X. So here the reflection P is just xyz equals to xy minus z. So now we can try and find out the reflection matrix. So for that need, we'll take our standard basis in R3, which is 1, 0, 0, 0, 1, 0, and 0, 0, 1. So now we can see P of 1, 0, 0 is 1, 0, 0. P of 0, 1, 0 is 0, 1, 0. And P of 0, 0, 1 is 0, 0, minus 1. So the reflection matrix P with respect to the standard basis is just the matrix 1, 0, 0, 0, 1, 0, and 0, 0, minus 1. So from here you can see that trace of P is just the sum of the diagonal elements because it's a diagonal matrix. So it will be 1 plus 1 minus 1, which is 1. And determinant of P is the product of the diagonal elements, which is minus 1. So according to the question, the answer should be 2 times 1 minus 3 times minus of 1. So it should be 2 plus 3 equals to 5. Now if the question is correct, the answer should be 5. So now we can ask another question, like since we have taken only a particular two-dimensional subspace, what about in general two-dimensional subspace? So we're gonna now answer this question. So what happens when S is any two-dimensional subspace? Any two-dimensional subspace instead of the xy plane, which is also a two-dimensional subspace, but that is a particular two-dimensional subspace we have taken to answer this question, right? So if S is any two-dimensional subspace, then the reflection through the two-dimensional subspace we can easily define. But before that, we have to understand what is a reflection. So a reflection means a reflection through a two-dimensional space means uh, if a point belongs to the same space, then the reflection will be the same point. But if that point does not belongs to the same subspace, to the subspace given two-dimensional subspace, then the reflection will be nothing but the flip, like you just flip the point to the opposite side and you'll get the reflection, right? So for example, in the above two-dimensional space x, y, and 0, such that x and y in R. So let us see the point so the reflection was defined like this: x, y, z equals to x, y, and minus z. So that means the reflection of suppose the point 1, 1, 1 will be 1, 1, and minus 1. Now what's going on here? So first try to see that 1, 1, and 1 can be written as 1, 1, and 0 plus 0, 0, and 1. Correct. So now let us call it A, and let us call it B. So, and let us call it C. So then try to see that the reflection of A will be A, because we said uh, if that point belongs to the space, then the reflection will be the same point since A belongs to S. Now B does not belongs to S clearly. So the reflection of B will be nothing but minus of P. So P of C will be P of A plus B, which is P of A plus P of B, which is A minus P. Now A was 1, 1, 0 minus 0, 0, 1. So 1, 1, and minus 1. So we can see that we got our reflection of 1, 1 was 1, 1, 1 as 1, 1, minus 1. So that means now we have now got an understanding that how to define the reflection through a two-dimensional subspace in R3, right? So if S is a two-dimensional subspace such that dimension of S is 2, then by orthogonal decomposition, uh, this R3 can be written as S direct sum of S perpendicular. Correct. So that means given A belongs to R3, we can find B and C in S and S perpendicular such that A equals to P plus C. Now, what is S perpendicular? So S perpendicular is nothing but the orthogonal projection, I mean orthogonal complement of S. So that is set of all vector P in R3 such that the product B comma X is 0 for all X in S. So this is the orthogonal decomposition or orthogonal complement. And so, and this is also in a subspace of R3. Now, since the dimension of S is 2, dimension of S perpendicular will be 1. So now we just stated that the reflection of the same point will be the same point, the B, and the reflection of the other point C, which does not belongs to S, will flip and will go to the opposite side of the point, and it will be just negative of that point. So the reflection of C will be minus of C. So given any point A in R3, which can be written as a sum of B plus C, has a reflection formula through this two-dimensional space as reflection at B plus reflection at C, which is P minus C. So if S is any two-dimensional subspace in R3, then P a reflection from R3 to R3 through S is defined like this: P of A equals to P minus C, where A equals to P plus C, where P belongs to S, C belongs to S perpendicular, and A belongs to R3. Okay, so now we can find out the eigenvalues of P. So first try to see that A belongs to S will imply A equals to A plus 0. that means the reflection at A is A minus 0, which is A, which is 1 times A. So that means 1 is an eigenvalue of A, of P. Again, dimension of S is 2. So this will imply uh, there are two linearly independent eigenvectors eigenvectors A1 and A2 such that P of A1 is A1 and P of A2 is A2. So one has algebraic multiplicity as 2. Okay, so now if A belongs to S perpendicular, then A also can be written as 0 plus A. And the reflection at A will be 0 minus A, which is minus A. So this is implying that, so this is minus 1 times A. So minus 1 is an eigenvalue of P. But since A belongs to S perpendicular and dimension of S perpendicular is 1, so this is implying minus 1 has algebraic multiplicity 1. So we got 3 eigenvalues of P as 1, 1 and minus 1. So now we can see that trace of P is 1 and determinant of P is minus 1. So I hope this question is clear now, and see you in the next question. Thank you.